A single chip smaller than your fingernail can hold more transistors than there are stars in the Milky Way. Apple's newest chip packs 134 billion of them, each one thousands of times thinner than a human hair, switching on and off billions of times every second. If you could set one of those transistors next to a red blood cell, the blood cell would look like a boulder. It starts as nothing more than ordinary sand. By the time it's finished, it will have passed through some of the cleanest rooms and the most expensive machines ever built by human beings. This is the complete story of how a microchip is actually made, from raw silicon to the most complex object humans have ever mass-produced. 1958, Jack Kilby builds the first integrated circuit, the size of a postage stamp. Months later, Robert Noyce builds a better version out of silicon. Both are credited as co-inventors of the microchip. And this one idea, cramming an entire circuit onto a single piece of material, created the modern world. Silicon is what's called a semiconductor, a material that can be tuned to either conduct electricity or block it, depending on tiny, precisely placed impurities added to it. Add one kind of impurity and it carries a surplus of electrons. Add another and it carries a deficit. Sandwich the two together and you get a transistor, a microscopic switch that flips on or off depending on a tiny electrical signal. Silicon earned this job partly because it's the second most abundant element in Earth's crust, and partly because it naturally forms a stable, glass-like oxide layer that makes it far easier to shape at a microscopic scale. That tunability is the whole trick. It's what lets engineers build billions of these switches, wired together, on a single sliver of material no bigger than a coin. It starts as ordinary sand, silicon dioxide, one of the most common materials on Earth. It's melted down and chemically refined, first into metallurgical-grade silicon that's about 98% pure, then refined again and again into electronic-grade polysilicon, 99.9999999% pure. Engineers call it 9 nines. To put that in perspective, that level of purity is roughly equivalent to a single grain of sand's worth of impurity spread across an entire beach. At that purity, there's barely a stray atom left in the entire batch, because the structures being built on top of it are only a few atoms wide, and even one contaminant in the wrong place can break the whole device. That purified silicon is melted again, and a tiny seed crystal is dipped into the surface and slowly pulled upward while rotating. The Czochralski process. Atom by atom, the molten silicon freezes onto the seed in perfect alignment, growing a single, flawless crystal ingot that can stretch over 6 feet long and weigh hundreds of pounds. The industry has grown these ingots larger and larger over the decades, from just a few inches wide in the early days to the 300-millimeter giants standard today, because a bigger wafer means more finished chips out of every single slice. That ingot is sliced, like a loaf of bread, into thousands of paper-thin wafers, each one thinner than a credit card, before being ground, etched, and polished to a mirror finish. From here, every wafer moves into a clean room, and not the kind you're picturing. Top chip fabs run ISO Class 1 environments, where the air is filtered up to 3.5 million times cleaner than the air outside. A single speck of dust is a boulder next to a transistor. Entering one means passing through an air shower and a strict gowning routine. Gloves, goggles, and a hood. Every single time, no exceptions, even for the engineers who designed the place. Technicians suit up head to toe in what's nicknamed a bunny suit, because a human body shedding skin cells is one of the biggest contamination risks in the entire building, and one stray particle landing in the wrong spot can ruin a wafer worth thousands of dollars. Now comes photolithography, the step that actually draws the circuit. The wafer is coated in a light-sensitive chemical called photoresist. Then a mask carrying the chip's circuit pattern is placed above it, and the whole thing is exposed to extreme ultraviolet light with a wavelength of just 13.5 nanometers. Each layer has to align with the one below it to a precision smaller than a single atom's width, repeated dozens of times across one chip. The machines that generate and focus that light are built by a single Dutch company with a near monopoly on the technology, and they cost around $380 million each, more than some commercial airliners, just to print a pattern smaller than a virus onto a disk of silicon. Wherever the light struck the resist, it dissolves away in a developing bath, exposing bare silicon underneath. That exposed silicon is then carved by plasma etching, cutting the circuit pattern directly into the wafer. Ion beams are fired at precise points to implant the doping impurities that turn ordinary silicon into functioning transistors. Later layers add a web of ultra-thin copper wiring, stacking directly on top of the transistors to connect billions of switches into one working circuit. The entire cycle repeats: lithography, etch, dope, deposit, again and again, building up as many as 100 stack layers in a process that adds up to roughly 1,400 separate steps for a single wafer. Before a wafer is ever cut apart, it goes through electrical testing while it's still one solid piece. A machine called a wafer prober lowers dozens of needle-thin contacts onto each individual die and runs it through a battery of tests, chip by chip, sometimes thousands of dies per wafer. Not every die survives the process perfectly. Some will fail and get marked with an ink dot, a practice going back decades that gave the term bug its modern meaning. The percentage of dies that pass is called the yield, and even a few extra percentage points of yield can be worth billions of dollars to a chip maker. Only the chips that pass move forward. A diamond-tipped saw then slices the wafer apart into individual, finished dies. Each surviving die is picked up, placed onto a small substrate, and connected using wires thinner than a strand of spider silk. Or, in more advanced chips, tiny solder bumps flip directly face down onto the substrate for an even shorter connection. Depending on the chip's job, it might end up in any of dozens of different package shapes, some designed purely to pull heat away from the silicon as fast as possible. The whole assembly is then sealed inside protective packaging, the black rectangle with metal legs or pads that you'd actually recognize if you pulled one off a circuit board, protecting the fragile silicon inside and giving it a way to connect to everything else in the device it's headed for. Intel's first commercial processor, released in 1971, held about 2,300 transistors. Today's flagship chips exceed 100 billion. That's roughly a 50 million times increase in about 50 years, on effectively the same size sliver of silicon. This trend is named after Intel co-founder Gordon Moore, who predicted back in 1965 that transistor counts would roughly double every couple of years, a prediction the industry has chased ever since. Engineers are now approaching the physical limits of how small a transistor can get, down to just a handful of silicon atoms across, which is why chip makers have started stacking transistors vertically instead of just shrinking them flatter and flatter. Your phone, your car, your fridge, your thermostat, your pacemaker if you have one, every one of them runs on chips built through this exact same process. Some chips are simple enough to run a microwave. Others contain more computing power than entire data centers held just a couple of decades ago. Even objects that don't look remotely digital, toothbrushes, running shoes, greeting cards that play music, increasingly have a tiny chip buried somewhere inside them. It's the quiet infrastructure sitting behind almost every modern convenience, hiding in plain sight inside nearly everything you touch, and most people go their entire lives without ever seeing one up close. Start to finish, a modern chip takes about 26 weeks to manufacture, passing through nearly 1,400 process steps along the way. A single leading-edge fab costs somewhere between $20 and $45 billion to build, more than most stadiums, airports, or skyscrapers on Earth. And a single fab can process tens of thousands of wafers a month, each one yielding hundreds of individual chips. Just 3 companies currently manufacture the world's most advanced chips, making this one of the most concentrated and strategically important industries on the planet. All trace back to an idea 2 engineers had, independently, within months of each other, in 1958. From a grain of sand to 100 billion transistors, that's how a microchip is really made. It's a process most of us rely on hundreds of times a day and almost never think about. Thanks for watching. Subscribe for more deep dives into how the everyday and not so everyday things around us are actually made. Comment below, which piece of technology should we take apart next?